Okay, you're here to learn or review about RC circuits. So if you know anything, pause the video right now and draw a simple RC circuit. Just construct one yourself, pause the video, and come back. Okay, what you should have is three circuit elements: a battery or a power supply or a source of EMF, a capacitor, and a resistor. And I put in a 3-position switch. A switch can be open in position 1, closed in this position 2, and closed here in this position 3. And if you're familiar with this circuit, you know why I did that. So an RC circuit is a simple series circuit of 3 circuit elements. Now we want to understand the behavior of this circuit from the time what happens over time when I close the switch to position 2, because right now nothing's happening. So generally we start with the capacitor uncharged and the switch open. So what will happen when we close the switch? Before we talk about that, let's review what we know about capacitors. So I want you to write down the capacitor equation for the relationship between capacitor charge and voltage, and the resistor equation for the relationship between voltage, current, and resistance. So write those down on the side. So here we are. To understand this circuit, we go to our definition of capacitance, which is capacitance is the ratio of charge to voltage. If we want the voltage across a capacitor, it will be equal to the charge on the capacitor divided by the capacitance. So we'll need this. This is one equation that we can rearrange, right, 3 different ways. The definition of resistance is the ratio of voltage to current. When we rewrite it, we get Ohm's law. So when we're dealing with the resistor, we want to use Ohm's law. And what we'll do to make things clear is we'll put a VR and a VC so we know what voltages we're talking about. So close the switch from position 1 to position 2, pause the video, and give yourself a minute to think about what's going to happen when we move the switch from position 1 to position 2. What's going to evolve over time in the circuit? See if you can answer that question before you listen to me. And just so it's clear, the capacitor starts uncharged. Right? There's no charge on the capacitor when we start. That should be stated. Okay, I rearranged things to create some space. So in a simple sense, what happens is the battery will cause current to flow onto this plate, charging this plate positive, and charge will flow off of this plate, leaving it negative. Remember, I'm talking about the movement of positive charge because that's current. It's really electrons going the other way, but we won't get stuck on that right now. So positive charge, a current moves through the battery, charging this plate positive. Positive charges move away and through the battery, the charge pump, leaving this plate negative. And so over time, the capacitor charges. So it goes from 0 to some final charge, and the place at which it will stop charging is when the capacitor reaches the voltage of the battery. So while the capacitor is charging, there's current going through the resistor. But when the capacitor gets fully charged, and this is 12 volts and the battery is 12 volts, there can be no more current. Because if there's current flowing, the battery would continue to charge, and it won't charge past 12 volts for a number of reasons. The simplest is that if the capacitor were bigger than 12 volts, then it would charge the battery. So it's going to charge to 12 volts and stop. Now the best way of visualizing this is to create 4 graphs of what's happening at the capacitor and the resistor, and those 4 graphs will be the voltage across the capacitor, the charge on the capacitor, the voltage across the resistor, and the current going through the resistor. So let me go pause the video and I'm going to change the drawing. Okay, there's a lot on here. Let me walk you through what I did. I put a voltmeter across the capacitor to read the voltage across the capacitor. This is like you did in lab, right? You put a voltmeter across the resistor, and we measured the voltage across the resistor. And then what we didn't do in lab is we put an ammeter in series in the circuit, so the current coming out of the resistor and going back to the battery will all pass through the ammeter, and so that's going to read the current through the resistor. And we don't have a meter for the charge. We'll calculate the charge on the capacitor using our capacitance equation later. Okay, so what we do know is that the capacitor starts uncharged. So we know that the voltage on the capacitor will be 0 if there's no charge on the capacitor. So this is going to start at 0, and it's going to charge to the battery voltage. Let's put a number in there. Let's make it 10. So it's going to charge to 10 volts. So it might not be obvious, but it's going to charge faster in the beginning when the capacitor is empty, and then the rate of charge going onto the capacitor is going to slow down till it reaches its final maximum value, and the voltage is going to do the same thing. It's going to follow it. The voltage in the charge follows it. It charges quicker in the beginning and then gets less and less and less and less. A good example that would follow this same behavior would be, imagine taking a cold glass of water out of the refrigerator and putting it on the kitchen counter. The cold glass of water is going to heat up fast in the beginning, but as it approaches the temperature of the room that it's in, it's going to very, very slowly come into equilibrium at that temperature. The same mathematics, the same physics describes this, and the equation that describes this you're familiar with. So anytime we have this charging behavior, the equation is going to be the same. In this case, the voltage across the capacitor is going to start at 0. If t equals 0, e to the minus 0 is 1, and 1 minus 1 is 0. This will be 0. But as time passes, this term will get smaller and smaller. It's a negative exponential, and this will approach 1. So after some period of time, the e to the minus t over the time constant becomes 0, and this just becomes Vmax. And that's the behavior, that's the charging behavior. And if you wanted to describe this behavior, you would just put QC, or the charge on the capacitor, is equal to the maximum final charge on the capacitor times this same term. Let's put some numbers in so we can have numbers here. Okay, so I gave the resistor a value of 5 ohms. I gave the capacitor a value, a little hard to read, 4 millifarads, 10 to the minus 3 farads. The battery's 10 volts. So we can chart, this starts at 0, but it's going to go to the maximum value. So if we go up to this equation, and we rewrite that, go and calculate what Qmax is, what the final value is. Use this equation to do it. Pause the video and do it. You can all do that. Okay, so taking this, either one of these equations and rewriting it, we get that the maximum charge on the capacitor will be the capacitance charge times the maximum voltage, and since that's 10 volts and this is 4 millifarads, we end up with a maximum charge of 40 millicoulombs. That's what it's going to charge to. And this equation would give us those values. Now, the Vmax we know, the time is just the time as it passes, but there's this time constant that I haven't talked about yet. This controls, right, whether it goes up very quickly or it happens over a longer period of time. That's why it's called the time constant. And most of you probably already know that the rate at which it charges, if you think about it logically, it depends on the capacitor and the resistor. So a bigger capacitor will take longer to charge, and a bigger resistor will slow the current down and make the charging take longer. So that's the logic. It comes out of the solution of differential equation. We won't get into that. But the logic, the physics part of it is that a bigger capacitor will take longer to charge, and a bigger resistor will lengthen the charging time as well. And so we have that relationship, which is very important, that the time constant, that tau, equals just the product of R and C. And since this is time, the time constant has to have units of seconds, and strangely enough, if you multiply ohms times farads, the result is seconds. Now, what's happening at the voltmeter across the resistor, and what's happening at the ammeter? In other words, what are these graphs going to look like? So pause for a second and see if you can answer that question. So what you should come up with is that in the beginning, when the charge is rapidly flowing onto the capacitor, the current is high, and when the charge stops going onto the capacitor, the current goes to zero. So this is going to decay exponentially. And the voltage has to follow the current, because the voltage across the resistor is simply a product of the current. So the voltage and the current, if the current is high, the voltage is high. If the current is zero, the voltage will be zero. And so these two things are going to do the opposite, kind of the mirror image. If we put a mirror here and reflect it down, you get the mirror image of that. And so the current falls off quickly and then gradually goes to zero, and the voltage, and you saw this in lab, the voltage across the capacitor falls off quickly in the beginning and then very slow at the end. Remember, when you were reading the meter, it was difficult to read in the beginning, but at the end it didn't change much. And this would be like, okay, you take a hot cup of coffee out of the microwave and you put it on the kitchen counter. It's going to cool very fast in the beginning, but as it approaches room temperature, the cooling slows down. The same equation will describe that behavior, whether it's a cooling cup of coffee or a discharging, this current, the behavior of the current through the resistor. Okay, so let's actually graph that. We have to find out what is the maximum current going to be. So to get that, this is Kirchhoff's law is going to come in. If we start with a 0 voltage on the capacitor and the battery's 10 volts, then at that instant of t equals 0, we have to have 10 volts on the resistor, because the sum of the voltages around the closed loop, Kirchhoff's law, have to be 0. So this is going to start at 10 volts, and in a similar way, it's going to decay, kind of, as I said, the mirror image of that upper graph. And the current is going to start at some maximum value. And so how do we get the maximum value of the current? We simply use this equation. Current will be the voltage divided by the resistance. So do it, 10 ohms divided by 10 volts divided by 5 ohms. So this is going to start at 2 amps. And in the same manner, at the same rate, it's going to decay to 0. So this is what you want to be able to do on the exam when I ask you to graph this behavior. And you should understand that this equation goes with the charging behavior, and if we take out the 1, we have the discharging exponential. So if we write it for voltage across the resistor, the form is the same. It's going to be VR, voltage across the resistor, equals Vmax. That's, in this case, the battery voltage. Whoops, let me do it. There it is. The voltage across the resistor is going to be the maximum voltage. So this starts at 10 volts. Remember, when we did the lab, we couldn't see it because it's only 10 volts for an instant. The meter can't even register it fast enough. And then it decays according to this term. This term will start when t is 0. This term is 1. When t goes to infinity, e to the minus infinity this goes to 0. So that describes this behavior. And if we wanted to write it for current, the current would be what? You can write it, right? I through the resistor equals I max, the 2 amps, times e to the minus t over RC. Okay, so what is RC and where does it fit onto the graph? We haven't graphed the time axis, and when I ask you to do the graphs, you will have to graph the time axis. There's where the RC comes in. So if we take the R and we multiply it by the C, we're going to get 5 times 4, which is 20, but since it's millifarads, it'll be 20 milliseconds. Let me write that down. There it is. The time constant is RC, so 5 ohms times 4 millifarads, 20 milliseconds. So where does that go on the graph? Well, the time starts at 0, and when the time gets to 20 milliseconds, then this equation will read 20 milliseconds over 20 milliseconds, because this is a constant, but the time starts at 0 and it goes 20, 40, 60, 80, so on. So when the time, the variable time, reaches the time constant, we have e to the minus 1. So I'm going to ask you to pause the video and go to your calculator and calculate e to the minus 1. So e to the minus 1 is 0.36788 and more. Rounded to 3 digits, it's 0.368. If we subtract that from 1, we get 0.632. And so after we get to 20 milliseconds, the charging will be about 63%, a little less than 2/3 of the way to the final value. And then if you go to 40 and 60, you'll get about 85%, about 86%, and then about 95%. But another way to think about it, interesting mathematical, if you're here, then the next time constant, it's going to go 2/3 of the remaining distance. That's where the 86% comes from. And then in the next time constant, when we go to 60 milliseconds, we're going to go 2/3 of what remains, and that gets us up to 95%. And so this is what you will use, this knowledge of the exponential charging and discharging function, to be able to do these graphs. You just go, you write down the time constant, 20, because you'll be asked to graph 3 time constants, 20, 40, 60. You put a point that's about a little less than 2/3 of the way up. It's good enough just to eyeball it. You don't have to calculate it. But after 3 time constants, it should be close to the top, but it should not be touching the top. If it's touching the top, then you're not being careful. And the same way decaying, if we do the 20 4060 for the voltage or the current, then this should have fallen about 2/3 the distance, or down to about 0.368 of that value. In other words, if this were 10 volts, this is going to be at 3.68 volts after one time constant. And then it goes that same roughly 2/3 again and again. And so this is how you can sketch out these graphs. And notice how I line them all up on top of each other. So you should practice this, because I will, on the midterm exam and maybe the final exam, ask you to be able to plot the behavior of this kind of circuit. Okay, two more things. Hang in there or come back later. Now we have the switch. I couldn't erase that, but that's gone. And now we have this lever or this switch, and we're going to close it down here so that this will be open, that'll be open, and the line going from here to here will be there, and everything else will be open. And then what's going to happen? So you should understand that when this is closed, now the battery's out of the picture, it's no longer there. The capacitor is charged to 10 volts, and the capacitor is going to discharge itself through the resistor. The time constant is going to be the same, but the voltage across the capacitor is now at 10 volts, and so it's going to decay. The charge on the capacitor, which starts at that value of 40 millicoulombs, will decay, same time constant. And the current, which had gone to 0, will instantaneously jump to the 2 amps, as the voltage across the resistor has to be equal and opposite to the voltage across the capacitor. So if the voltage across this is 10, this would be a -10. But if usually we just plot the magnitude. And the other thing that I didn't mention, and you should notice, is that since the sum, going back to the first part, since the sum of the voltages always have to be 0, these two voltages in the charging cycle all have to add to 10. So when the voltage across the capacitor is 2, the voltage across the resistor will be 8. And when the voltage across the capacitor is 9, the voltage across the resistor will be 1. They always add to 10. And during the discharge cycle, these two have to be equal and opposite, because the sum of the voltages around this loop, when this is closed, have to be 0. That's Kirchhoff's law. And so the equation that describes the discharging behavior is a discharging equation for all circuit elements and all these values. I'm not going to go through that in detail. Okay, the last thing is, and there will be some questions, supposing I say, well, how long does it take to get half charged? Or how long does it take to get 95% charged? Or what's the charge on the capacitor at 30 milliseconds? So for questions like that, you have to use either this equation or this equation to calculate them. So let me just demonstrate one or two of those, just in case you have any questions when you get to the assignment on how to do that. And then I'll end the video. Okay, first question. What will be the charge on the capacitor after 10 milliseconds? Now think about the physics. We know it's going to be 63% charged at 20 milliseconds. So it's going to be less than 63% charged out of the 40 millicoulombs. So use the equation and calculate QC at 10 milliseconds. Just do that and come back. Okay, did you get that? Good. Remember, we said it has to be less than the 2/3. The 2/3 is about 25. So you see it's more than halfway toward what it's going to be at 20 because it's going faster in the beginning, right? So that's value seems correct. Okay, now find out how long it's going to take for the capacitor to be 90% charged, to reach 90% of its final value. And since I told you it takes 3 time constants to get to 95% and 2 to get to about 86%, it should be somewhere between 40 and 60 milliseconds. See if you can do that. Try calculating that. Okay, this one's a little trickier if you haven't done this in a while. So we need to get the t out of here. So what I do, I divide by Q max. I subtract 1 from both sides. I get this. I don't want the minus sign here. I want to rearrange it, so I multiply by a -1 and turn it all around. So I get e to the minus t over RC equals 1 minus that. The QC, remember, we want it to be 90% charged, so there's no sense in taking 90% of 40 and then dividing by 40, the Q max. It's just QC over Q max when it's 90% will be 0.9. So we have 1 minus 0.9, which is 0.1. And we take the natural log. Oh, we have to take the log of both sides, right, to get rid of the e. Forget that. That's where the log comes in. And so the log of 0.1 times RC gives us 46.1 milliseconds, which is what we were expecting. That's a way to confirm that we didn't make a mistake, right? Because we knew it was going to be between 40 and 60 based on what we know about these circuits. And so there it is. So we can have confidence that that's the correct answer. Okay, I think you're good to go on the assignment, and just be prepared to be able to do those graphs when it comes to the exam next week. Okay, good job.